When airports stop telling time, they're admitting the schedules no longer work. On September 4, 2023, passengers at Denver International Airport began noticing something unsettling. The large digital clocks that had displayed gate times, departure schedules, and current time throughout the terminal were systematically disappearing. First from gate C42, then from the main concourse displays, then from departure lounges across multiple terminal sections. Within 6 weeks, DEN had quietly removed or disabled over 200 public time displays, without official announcement or passenger notification. Denver wasn't alone. Frankfurt Airport removed 150-plus clocks during routine maintenance that never resulted in replacement. Heathrow disabled terminal time displays during renovation projects that targeted clocks specifically while leaving other infrastructure unchanged. Charles de Gaulle, Amsterdam Schiphol, and Singapore Changi implemented similar clock removal programs disguised as modernization initiatives. The pattern wasn't random infrastructure updating or aesthetic redesign. Airports across multiple countries were systematically eliminating time reference points as psychological preparation for transportation system breakdown, where schedule reliability had become mathematical impossibility. When passengers can't see time, they can't measure delays, reducing stress during increasingly frequent flight disruptions. Understanding airport clock removal requires recognizing systematic breakdown of aviation scheduling mathematics that has made on-time performance impossible to achieve through conventional operational improvements. Flight delay rates, cancellation percentages, and schedule reliability have deteriorated beyond thresholds where time displays create passenger panic rather than helpful information. Mathematical analysis of global aviation performance reveals systematic breakdown across all major metrics that measure schedule reliability and operational efficiency. On-time performance has declined from 85% in 2019 to 67% in 2023, while average delay times have increased from 14 minutes to 47 minutes per affected flight. These deteriorations represent mathematical impossibility of maintaining schedule integrity. The mathematical foundation of aviation operations depends on coordination timing across thousands of variables, including aircraft availability, crew scheduling, air traffic control capacity, runway utilization, weather conditions, and passenger processing efficiency. When any component experiences degradation, schedule mathematics become exponentially more complex and unreliable. Current aviation system stress has reached mathematical thresholds where component failures cascade through interconnected scheduling networks, creating systematic delays that cannot be resolved through operational adjustments. Schedule recovery mathematics indicate that delay propagation has become self-reinforcing, making punctuality restoration impossible through conventional management techniques. Pilot shortage mathematics represent fundamental constraint on aviation system capacity because flight operations require specific crew certifications that cannot be quickly replaced during personnel shortages. Global pilot shortage exceeds 12,000 qualified pilots currently, with projections suggesting 50,000-plus shortage within 5 years based on retirement rates versus training capacity. The mathematical implications of pilot shortages create systematic flight cancellations because airlines cannot maintain published schedules when crew availability falls below operational requirements. Pilot shortage mathematics force schedule reductions that make advertised departure times meaningless while creating uncertainty that clock displays would highlight and amplify. Air traffic control capacity represents another mathematical constraint that limits aviation system throughput, regardless of aircraft or crew availability. ATC facilities operate with aging equipment and reduced staffing that creates bottlenecks affecting schedule reliability across entire regional networks. Mathematical analysis of ATC capacity indicates systematic inability to process current traffic volumes during peak periods, forcing flight delays that cascade throughout daily scheduling cycles. ATC mathematics demonstrate infrastructure limitations that cannot be resolved through airline operational improvements, making schedule adherence impossible during high-volume periods. Runway capacity constraints create additional mathematical limitations because airport infrastructure development has failed to keep pace with traffic growth over decades. Major airports operate at mathematical capacity limits, where any disruption creates systematic delays affecting hundreds of flights across multiple airlines simultaneously. The mathematical relationship between runway capacity and flight volumes indicates systematic overutilization that makes schedule recovery impossible when weather, maintenance, or operational disruptions affect airport operations. Runway mathematics demonstrate infrastructure constraints that guarantee schedule breakdown during any significant disruption events. Aircraft maintenance requirements have created systematic availability problems because aging fleets require increasing maintenance time, while new aircraft delivery delays prevent fleet renewal at rates necessary to maintain schedule reliability. Aircraft availability mathematics indicate systematic capacity constraints that force schedule adjustments regardless of demand levels. Mathematical analysis of aircraft utilization reveals systematic degradation in fleet reliability that creates unpredictable maintenance requirements affecting schedule planning. Maintenance mathematics force conservative scheduling that reduces capacity utilization while creating uncertainty that makes published schedules unreliable guides to actual departure times. Weather impact mathematics demonstrates systematic increase in disruption frequency and severity that affects aviation operations beyond historical planning parameters. Climate change effects create weather patterns that exceed operational tolerances more frequently while lasting longer than traditional weather delays. Mathematical modeling of weather disruption patterns indicates systematic increase in schedule unreliability due to meteorological factors beyond airline control. Weather mathematics suggest traditional schedule buffer times are inadequate for current disruption frequencies, making punctuality impossible during increasingly common severe weather events. Passenger processing efficiency has degraded systematically due to security requirements, staffing shortages, and infrastructure limitations that create bottlenecks affecting departure timing regardless of aircraft and crew readiness. Passenger processing mathematics indicate systematic delays that propagate through scheduling systems. Mathematical analysis of passenger flow rates reveals systematic degradation in processing efficiency that creates departure delays independent of aviation operations. Processing mathematics demonstrate ground infrastructure constraints that affect schedule reliability through systematic passenger handling bottlenecks. Supply chain disruptions affecting aviation fuel, spare parts, catering services, and ground equipment create systematic operational uncertainties that make schedule adherence impossible to guarantee through airline planning processes. Supply chain mathematics indicates systematic reliability degradation across multiple operational dependencies. Mathematical assessment of aviation supply chain reliability reveals systematic vulnerabilities that create unpredictable operational constraints affecting schedule performance. Supply chain mathematics demonstrate external dependencies beyond airline control that make schedule guarantees impossible during supply disruption periods. The psychological impact of visible time displays during systematic schedule breakdown creates passenger stress and anger that airports have determined exceeds the informational value of time reference. Clock removal represents institutional recognition that schedule reliability has deteriorated beyond levels where time information helps rather than harms passenger experience. Mathematical analysis of passenger behavioral responses to delay information indicates systematic stress escalation when delays become frequent and unpredictable. Passenger psychology mathematics suggests that removing time references reduces anxiety during systematic schedule breakdown while maintaining passenger cooperation during extended disruption periods. Historical precedent for infrastructure time removal appears during systematic breakdown periods when organizations eliminate performance measurement displays that would reveal operational failure. Soviet factories removed production timing displays during economic breakdown. Hospital emergency departments remove wait time displays during systematic overcrowding. Similar psychology applies to airport operations. Mathematical pattern recognition indicates institutional behavior where organizations remove measurement displays when performance has deteriorated beyond recovery capacity through operational improvements. Time removal mathematics suggests systematic recognition that schedule performance cannot be restored to acceptable levels through conventional aviation industry interventions. International aviation coordination breakdown creates additional systematic constraints because global flight networks depend on synchronized scheduling across multiple time zones, regulatory systems, and operational standards. International coordination mathematics indicates systematic deterioration in network reliability that affects domestic schedule integrity. Mathematical analysis of international aviation networks reveals systematic coordination failures that create delay propagation across continental flight systems. International mathematics demonstrate network effects where regional breakdown affects global aviation scheduling regardless of local operational efficiency improvements. Regulatory compliance requirements have created systematic operational complexities that reduce aviation efficiency while increasing schedule uncertainty through administrative processes beyond airline control. Regulatory mathematics indicate systematic increase in compliance burden that affects operational capacity and schedule reliability. Mathematical assessment of regulatory impact on aviation operations reveals systematic efficiency degradation through administrative requirements that consume operational resources while creating schedule uncertainties. Regulatory mathematics demonstrate bureaucratic constraints that affect schedule performance regardless of airline operational capabilities. Economic pressures affecting airline industry profitability have forced operational cost reductions that eliminate schedule buffer times and redundant capacity that previously provided schedule reliability insurance. Economic mathematics indicate systematic elimination of operational margins that made schedule recovery possible during disruption events. Mathematical analysis of airline economic constraints reveals systematic reduction in operational resilience through cost optimization that eliminates schedule reliability mechanisms. Economic mathematics demonstrate financial pressures that force operational efficiency improvements incompatible with schedule dependability during stress conditions. Technology system failures affecting reservation systems, communication networks, and operational coordination platforms create systematic disruptions that make schedule coordination impossible across complex airline networks. Technology mathematics indicate systematic reliability degradation in digital systems essential for aviation operations. Mathematical assessment of aviation technology reliability reveals systematic vulnerabilities in digital infrastructure that create operational uncertainties affecting schedule performance. Technology mathematics demonstrates systematic dependencies on digital systems whose failure makes schedule coordination impossible, regardless of human operational capabilities. Airport clock removal represents institutional acknowledgement that aviation system mathematics have deteriorated beyond thresholds where schedule displays provide useful information rather than passenger frustration amplification. Clock elimination indicates systematic breakdown recognition rather than cosmetic infrastructure updating. Mathematical progression toward aviation system breakdown suggests schedule reliability will continue deteriorating as infrastructure constraints, personnel shortages, and operational complexities exceed solution capacity through conventional industry interventions. Schedule breakdown mathematics indicate systematic problems requiring fundamental restructuring rather than incremental improvements. The psychological warfare aspect of clock removal represents institutional strategy for managing passenger expectations during systematic operational breakdown by eliminating measurement references that would reveal performance deterioration. Time elimination mathematics suggest acceptance of schedule unreliability as permanent operational condition. Understanding airport behavior as breakdown preparation rather than passenger service improvement provides insight into institutional recognition of systematic aviation problems that cannot be resolved through conventional operational enhancements. Clock removal indicates institutional preparation for permanent schedule unreliability rather than temporary operational difficulties. Current aviation system mathematics suggest systematic breakdown approaching across multiple operational dimensions simultaneously, creating compound effects that exceed industry solution capacity through traditional management approaches. Schedule mathematics indicate fundamental system restructuring necessary rather than incremental operational improvements. The cascade effects of aviation breakdown extend beyond airline industry because modern economies depend on reliable air transportation for business operations, supply chain coordination, and economic activity that requires predictable travel scheduling. Aviation mathematics indicate systematic economic impacts when transportation reliability deteriorates beyond business planning capabilities. International economic coordination depends on aviation schedule reliability for business travel, cargo transportation, and commercial relationships that require predictable transportation timing. Aviation breakdown mathematics suggest systematic economic disruption when transportation systems cannot provide schedule dependability for commercial planning purposes. Clock removal represents visible indicator of systematic infrastructure breakdown that affects broader economic systems beyond aviation industry. Time elimination mathematics indicate institutional recognition of systematic problems that extend throughout modern transportation dependencies essential for economic functionality. When airports stop telling time, they're acknowledging mathematical reality that schedule coordination has become impossible through conventional operational methods while preparing passenger psychology for systematic breakdown conditions. Clock removal indicates institutional acceptance that aviation scheduling mathematics cannot be restored to reliable functionality through industry interventions currently available. The systematic elimination of time displays across multiple international airports represents coordinated recognition that aviation system mathematics have deteriorated beyond recovery through conventional improvements, requiring fundamental restructuring of passenger expectations rather than operational performance restoration.